see how that all plays out. Yeah, I guess we'll get started. I'd like to introduce our first speaker, Abigail Burt of the OGS.
Thank you. Okay. You just keep going.
Okay, here we go. Thank you so much. I am very, very pleased to be here, and I'm going to see if we can trim my presentation on the fly. But you know how it goes with shortcuts, right? Oftentimes they end up as long cuts, so we'll see how that goes. Oh dear, it's not starting off well. Kayla, we have a bit of a thing. Yeah, okay. We're just going to regroup for a moment because we have slide number, I don't know, 7 coming up first. Oh dear. Sorry about that, everyone. So while we're getting started, I'm going to be talking to you a little bit about our preparations for doing some geophysics in the city of Guelph area. As you know, we have been doing 3D modeling in Southern Ontario, Southwestern Ontario, since 2002. We have about 5 projects that are either completed or are ongoing, and the most recent project area to join our collection is in the Guelph area. And this one is a bit of a fill-in project that'll join up Orangeville, Fergus, region of Waterloo, and Niagara. Niagara is pending. We are hoping to be invited down into the Six Nations area to do a little bit more work so we can finish that one off. So, looks like we are in business. Okay, so there we go. A long cut, as I threatened. So today's presentation is all about how we get started for finding wonderful buried valleys and gorges, such as the one pictured here. And if you look down in the far lower right corner, you can see a person. So it's quite a big feature, but it can be difficult to detect if it is completely buried. So we're going to introduce the Guelph area really quickly now, a little bit of geologic context for the region, gravity 101, how does it work, and finally some very preliminary results. I just started to get some profiles on Friday, so hot off the presses. So I think we've done that. We know why we do 3D modeling. Okay, so here is the project area. We are covering up portions of Halton, Wellington County, Waterloo Region, City of Hamilton, and of course the City of Guelph. And I've highlighted the 401, that's that wobbly blue line, because it really shows just how built up this area is and how we have to be able to accommodate so many different competing demands on land use, whether it's for residential, commercial, or industrial development. Woo, now we're getting really excited there. We also have to be able to accommodate our natural environment, infrastructure, transportation corridors, and agriculture. So it's a busy area. And if we want to be able to plan appropriately, we need data. So looking very quickly at this drift thickness model, this is available from MRD 207, and Key, can you wave Key? Right at the back, he's got a demonstration, and he will show you how to be able to download all this great data from the brand new Geology Ontario Hub. It's new and improved. So looking at this drift thickness layer, thinner sediments near the escarpment are shown in green. Thicker sediments, which are in the Waterloo region, are in red. So we can see that there's a lot of different things that are going to be happening in this area. The black dashed line is the Niagara escarpment. Underneath the red star, we could, ooh, boy, what the heck? It's sensitive, everyone. It just likes me for some reason. Okay, underneath the star, we have the region of Waterloo, and several of the moraines in the area, Paris, Galt, as well as the Waterdown moraines, are underneath those white crosshatches. So those are where we have some locally thicker sediments. But of course, there are other locally thicker sediments which are not accommodated by some of these moraines, and those are highlighted by those blue arrows. So we need to come up for an explanation for those. And for that, we are going to hopefully, there we go, we're going to be turning our attention to the regional bedrock surface. This is also available in MRD 207, so see key for that. Now on this particular colored ramp, we have the higher sediment shown in red. As you get lower, you're going to go through the greens and blues and down into purple for the lows. And what you can see right away is that there are several really broad troughs, and this is just created by differential erosion of shales, evaporites, and carbonate rocks. And that information is available in MRD 219. Now I've put a geologic map on that smaller version down on the left-hand side, and you'll notice that I did not put a legend on it. And I didn't put a legend because I wanted people to start to think about what we're really showing when we're portraying geological information. Now, it sounds a little weird, but so many of us are in the habit of just calling up that key legend that comes up, all the different formations, but that doesn't necessarily mean a whole lot to some people. I know that the Guelph Formation is Vuggy Dolostone, but maybe other people don't. So delve into that data set and you can color things up however you like, and it'll look a little bit different. Okay, so moving right along. Here we go. If we look at the escarpment, you'll notice that there are a series of notches, and those are highlighted by those black arrows. And this is where things start to get really interesting. So if we look really carefully, we can see that there are a series of very deep and narrow valleys that extend back from those notches. And there are also some narrow valleys that are further away from the escarpment. And as most of us here today know, these valleys and their fill are really important from a groundwater perspective. But the trick is trying to find them and drill into them. So zooming back in, and this time without the color ramp, we can see that the notches are highlighted by those green arrows, and the valleys are highlighted by the pink arrows. Let me just adjust things so we can actually see. There we go. Okay, so if we look really closely, we'll see that those valleys are more a series of dots than a nice clear line. And each one of those dots corresponds either with a single or a cluster of domestic water wells. And this was the primary data set that was used to create the surface. And as one would expect, people put their wells where they want them, like close to their house, as opposed to finding that valley for me. So if I want to drill down into that deepest part and get the best available information, we're going to need to find the central portion. And for that, we're going to be turning our attention to geophysics as just one of those tools. And if people are interested in finding a little bit more about the impact of a single incorrectly placed well or well record, I encourage you to check out Patty Meyer's 2013 presentation from our open house last year, and you can see that on the GSC Groundwater YouTube channel, that as well as all the other presentations. Okay, so the gravity surveys are just one way of finding out what is in the subsurface, and it's something that we've had quite good success with for our OGS surveys. So gravity surveys, just here's the 101, they measure density variations of the subsurface materials at individual stations. And this could be done either on a grid or along profiles. And that's the method we adopt in Ontario. We're confined to those roads. So it's important to keep in mind that when you're doing a gravity survey, it's measuring everything from the center of the earth up to surface. So once the survey has been completed and the data have undergone all the QA and QC, there's a lot of processing and reduction steps that have to get rid of everything except that part which we're interested in, which are the very small changes in density due to variations for the near surface materials. So for example, Dolostone has a higher density of sand, and so as the survey progresses along a road, we would expect to see a change in the gravity reading as you pass over a sand-filled buried bedrock valley. And that's an example there. That was over the Dundas Valley. That was one of the best responses I've seen, as you'd expect for a whacking great valley. And we were able to pinpoint what we determined to be the exact center and use that as incentive to drill, and it was wonderful. So there are, of course, complications. There are with everything. The first thing that we need to think about when designing a survey is whether or not there are going to be density differences between the various materials. So we need to think both about the density of the rock as well as the quaternary sediments. No density difference, no response. Now in some areas, we also have to keep in mind that karst will create potentially huge voids in the rock, and think about whether or not that is going to be enough to overshadow what could be quite a small valley. So it's worthwhile checking out the karst potential maps in GRS 5, and that was done by Frank Brunton, and I believe he's updating that. We also need to consider the size of the features we are interested in and how that will affect our station spacing, and in turn the cost. So if a feature that you're after is only a couple of 100 meters wide, you need to have quite closely spaced stations than a feature that's 1 to 2 kilometers across. And we've used both 50 and 100 meter spacings at various surveys. Then, of course, there's the potential complication of the road networks themselves. Roads that are perpendicular to a valley will yield a much better result than the one that crosses at an angle. And you can just see a bit of a representation of that with the figure that just popped up. Roads that run parallel to a valley are either going to miss it entirely, or else you're going to have a huge, long anomaly, which doesn't really tell you a whole lot. So selecting those roads and planning that survey comes down to a really careful assessment of the regional bedrock surface, thinking about the orientation of the valleys or the portions of them that are visible at surface, understanding joint and fracture patterns of the rocks in questions, or in other words, basically just an educated guess. And finally, while gravity surveys aren't affected by the anthropogenic features in the same way that some of the electrical methods, like overhead wires, we do have to consider heavy traffic. Both we don't want to get people hit, and of course vibrations. So some of the pitfalls and considerations. Oh, now it's not fast forwarding. There we go. So very quickly, we'll look at an example from the Rockwood Valley from the Orangeville-Fergus area to the north of Guelph, and this is available in GDS 1072. GDS simply stands for a geophysical data set. So these results provide a window into the type of response that we might expect in the Guelph area, as the bedrock lithology is similar, dolostone, and at least some of the quaternary sediments are the same. So here we can see the gravity anomaly for selected lines superimposed on top of a really violently colored regional bedrock surface, which emphasizes those dots. So here, the narrow black line are the survey lines. Those pale orangey things, those wedge shapes, those are the gravity anomalies. And basically, a really simple way of thinking about it, oh, now it's excited again. I drill where the biggest dip is. And there we go, aim for the dip. Drilling was very important in this area as it helped me to confirm the survey results. It also allowed me to characterize the valley fill, and it was an opportunity to collaborate with other organizations, in this case GRCA, to install a monitoring well. So if you're hearing a little bit about how these regional scale surveys could be better integrated into site-specific work, I would encourage you to tackle Jesse Brown. He's somewhere in the audience, I saw him today. He did some work on the Elora Buried Valley, so you can have a chat with him. So this brings us to one of the limitations of gravity surveys. They're great at providing insight into the shape of the valley itself, but it doesn't show you a whole lot about what the quaternary sediments look like. So for that, you might want to consider a shallow seismic survey. And this is an example of the work of the GSC, Barbara Dedeker, Heather Crow, and Andre Proujan. So seismic work with downhole geophysics, if you need to know the nitty-gritty details. So let's look at our area of interest. Now, the Guelph survey, shown in blue, was designed to fill in between several existing surveys, and yes, we are planning a compilation in the future. As you can see from our base map, the road orientations and built-up areas were quite a problem in this region, and we ended up selecting 17 roads that we felt would give the greatest chance of success. We used 50-meter station spacings following Barbara's recommendation and the work in Orangeville, and our final tally was about 3,400 stations. And a lot of details about the equipment, tie-in to base stations and such will be available in the upcoming geophysical dataset report. So finally, we get to focus on some very preliminary results. So these are they're still undergoing QA, QC, and processing, so things will look a little bit different in the final evaluation. But basically, this image is showing the calculated gravity, oh my goodness, anomaly at each station. Red and pink shows gravity highs, indicative of higher density material in the subsurface. Blues and green show where we have lower density material in the subsurface. So basically, rock highs and rock lows. Now, when we look very closely along those lines, you can see there are some color variations, and it's here that we hope to find some clues about the location of those buried bedrock valleys that we're after. So I find these variations easier to pick out when examining the profiles rather than the top-down view, and Sarab has provided some very preliminary profiles for us to look at today. So the paler lines show the roads where the readings were taken, and those darker blue areas show where there are lower density materials, so potentially our valleys. And the first thing we want to look for is to see evidence that the method actually worked in our area. So in the very far southeast, we can see a couple of spots on the quaternary map where rock, which is colored pink, is mapped at surface, and this is separated by organics, which are colored gray. So right away we know we've got some kind of valley. This one isn't buried, although it is filled. And sure enough, there is a bit of a gravity low, so we can be fairly confident that the method is working. Looking carefully at some of the other dips, whether they're large or small, we can see that some of them do correspond with modern rivers and streams. And this isn't going to be any real surprise, as of course any kind of pre-existing bedrock valley is going to influence glacial drainage patterns, deposition of sand and gravel, which is much easier for meltwater to erode. So before we get too excited on that front, we do have to acknowledge that having this more modern response can make things a little bit more difficult to sort out, and we don't want to get tricked into drilling anomalies that are related to those modern streams, or even things like alternating drumlins and wetlands. So in our final example, we're going to be looking at some very different anomalies along one area. Looking very carefully at the portion that's circled in black, we can see that there are very small changes in the gravity response, and those are likely related to topography, differences in density, so those drumlins and the overlying wetlands. But there are much larger anomalies which hint at other factors, and maybe these are some of the buried valleys that we're all interested in. So we're going to be hopefully resolving these questions in the coming weeks and months. So the takeaway from all this is that there are a lot of regional surveys that are already available as base information for planning your own work. We also need to understand some of the pitfalls and limitations, what gravity can actually show us. And that by using the most cost-effective geophysical methods, so bare bones, we can often answer some really good questions so long as we plan our surveys correctly. And of course, I'd like to encourage everybody to reach out to the experts we have at the OGS as well as the GSC for answering questions. So thank you.
So we just move right along.
See, does anybody have any questions?
If anybody has a burning question, you can ask now, or maybe just catch me at the break and we will keep things moving right along. Oh, I see a question at the back.
Would airborne gravity work for this kind of study, or is the sensitivity not there?
The problem with airborne, at least what we found, is in built-up areas, you have to be really careful. The ones that we've done were affected by overhead wires, so infrastructure. So when in a really built-up area, it can cause a bit of a problem. There's also differences in cost. But what we do is we look at the most cost-effective method for any particular area and the type of information that we're trying to get.
I'll add one thing to that. Also, it's very difficult to get permission to fly a bird over a built-up area.
Yes.
We looked at it for TRCA at one point, and yeah, you can do it over rural areas, but over built-up areas, they don't like towed birds.
Yeah, so Guelph, Waterloo, Kitchener, Cambridge, it would probably be a bit problematic. Thank you.